Hello, I'm going to talk to you about the solar system exploration, but of course focused on the exobiology. Just for you to know, if you want to contact me, it's rather easy. You have here my email address. You can contact me before, during or after, and I will try to respond to you as I do every time. The idea here is the following. You know what the space activity is, the space area. I think it's interesting to understand how things grew over the time. It started a little more than 60 years ago, so it's really my generation, I would say. I saw the first, or I hear the first beep beep from Sputnik. That was in '57. But what I want to focus on today is not really the space area per se, it's really where finally we start the exploration of the solar system. And that really happened only a few months later, when the Soviet Union, the same who did the Sputnik, decided not only to send a Sputnik around the Earth, but now to send a mission out of the Earth's gravity. It was the first time ever attempted, and it was a success. So that was in January '59. And really they opened the fantastic era of interplanetary journeys, trips, travels. And that's really the starting point of the space exploration of the solar system, because as soon as we knew that we could explore the outer body of the solar system, it really grew a lot of discoveries, as you know, but we'll go in details today on that. So the topic, of course, was at that time to demonstrate that we were able to leave the Earth gravitationally, and the target, of course, was the closest one, which was the Moon. So it was Luna 1, the Moon 1, we would say, who went there. And rapidly, the people understood that with space exploration, we could really do some exobiology in two ways. First, to know whether or not there are extraterrestrial life else than on the Earth. And that was one of the topics really emphasized as such from the beginning. And the second, of course, was to know whether or not we could have biological human beings or other beings capable of living in outer space. And dramatically, in a sense, the first body who went in space was only 1 month after the Sputnik, much before they even went to the Moon. In November '57, just 1 month after October, a small dog, Laika, went to space. They knew that it would not come back because they didn't have the capsule to come back, but they could verify that actually you could survive days, weeks actually, in space. Just to sum up what we just saw, the first Sputnik had only one mission. It was really to send telecommunication, beep beep, just to know whether or not we could communicate with something that would be out of the atmosphere, only 150 or 200 kilometers above our heads, and it was successful. So it's only because it's been demonstrated that we could communicate that space exploration really started. Human beings in space, as you know, they went to many places. The Soviets want really to practice what we call now the space station, first with the Salyut, then the Mir. They really had a plan that Korolev, the leader over there, really put together. And here you see actually a Russian cosmonaut on the ISS, where, as you know, Thomas Pesquet is in right now. And so what is important is to realize that up to the space era, up to the 50s and 60s, all the idea we had of the origin of the world, origin of life and everything, was only based on dogma. We didn't have any real observation that would validate the fact that there is extraterrestrial life. Actually, there was not even a single measurement saying it's not the case. We didn't know whether it was or it was not feasible to have extraterrestrial life. It was only based on dogmatic approach and not scientific approach. And as you will see, we are now entering the scientific era for that question. Because it was dogma, of course, the dogma evolved in space and time, from one location to the next, from one society to the next, and from a single society among the time. So, given the way and what was the origin of the dogma themselves, we found finally that this question of origin of life and life by itself has really evolved in space. One important thing that, and I think it's not well known, that the question of plurality of world, the fact that there is other, beyond the Earth and beyond even the solar system, places where life exists, started very, very long ago. And we have one record of that. I'm not saying it's the first one, it's the first that we have really. It's from Epicurus, as you know, a Greek philosopher. It was in the 4th century before BC. And his idea was rather simple. He conceived that the universe was infinite. And it was really a conception, no more than that. As you know, by the naked eyes, you see 1,500, 2,000 stars at most. It was fantastic that he extrapolated that for much beyond that, and he considered that universe should be and is infinite. And in a very important document that everyone should or could read at least, which is a letter to Herodote. Herodote, not the famous historian guy, it was one of his students who had that name. He wrote a letter to him, and you can really go to the letter to Herodote, and you will see that it's a very small document, and you will see that how Epicurus himself, just translating the infinity of space, considered that if there is infinite space, there cannot be an infinite number of life and inhabited planets, worlds. And actually, in the same document, he said there is, because the universe is infinite, there is necessarily an infinite number of inhabited worlds and an infinite number of non-habited worlds, which is a pure perfect definition of infinity, actually. So that's how it started. But as you know, rather rapidly, both first in Greece and then by all the monotheism, that's been cancelled. Plurality of world has been replaced by the fact that Earth has been created, and it has been created central, unique in the universe. And as you know, we have a lot of demonstration of that up to the centuries, up to the Renaissance. And the Earth was created during 6 days, as you know, and not only the Earth, but everything there, including humanity. But as you also know, probably humanity was created in the Bible on the 6th day, after the nature was created. So the idea that human beings do not belong to nature is really long-lived story. It really started from the Bible itself. So that was the story over centuries, because as you know, we had to wait the 16th century and Copernicus to propose something entirely different, and that's what we call that a revolution. Although, as you know, a revolution is something that goes back to its central point, so we should not call that a revolution, but still it's considered as a revolution, that he proposed that instead of having the Earth at the center should not be the Earth, but the central, even didn't say the Sun. I put the Sun here because everyone so know that. But it was so heretic that he only wrote that it was the center of the Earth's orbit, which of course is identical. But it was really so heretic that 1543, as you see here, which is the date of his death, he died is exactly the same year it's been published. This document was published the same year of his death. But that's really what the starting point. Actually, when you read the document there, Copernicus didn't change the fact that the stars are in a fixed sphere, and around the sphere and beyond the sphere there is a huge space dedicated to God. So he didn't want to go back to the infinity, and essentially he didn't change anything else than this fantastic proposal that all the planets just around the Sun. And of course, rapidly, because this demonstrated that the planet Earth was just a trivial planet, just around the Sun as the others, we had 4 or 5 others at that time, the Earth went back to standard generic instead of exemplary of something that would happen also other in space. So that's how finally the Earth has been proposed as a standard generic planet after it's been during 15th century a central unique world. And only a few years after Copernicus died, Giordano Bruno was born, and he was Copernican from the beginning. He studied, he was a priest also. He studied in different universities, Padova in particular, where the Copernicus stuff was, you could read that at that point. And he went one step further. He considered 2 things. One, he considered that stars and sun have the same nature, that the sun is a star and all the stars are sun. That's really a fantastic thing, because when you realize how long it has been to demonstrate that physically, of course by physics, But he said, I am not a physicist, I am not even a scientist, it's my way of thinking, and no one will never be able, he said, to demonstrate that. It's because of that, actually, that most of the scientists afterwards did not want to recommend even to read him, because they considered he was not a scientist. But what he proposed was really fantastic. And what he said, which is more than that, he said, well, I consider that the universe is infinite. Again, against what Copernicus even thought after all what the church imposed. He considered that back to what Epicurus proposed almost 2 million before, that he did not refer to Epicurus just proposing that there is an infinite number of stars and so an infinite numbers of suns, in a sense. As you probably know, because of that, he has been arrested in Venice, where he was hidden, and there has been a 7 years trial. Afterwards, he was burnt. And what is interesting is that the people wanted him to recuse, exactly as Galileo did afterwards, to say, okay, I was wrong, I should not have said that. And he accepted everything, including the Virgin and whatever they wanted him to accept. One thing he didn't want to say I was wrong is this question of infinite number of suns, the fact that there should be plurality of worlds. And so that's what happened there. He said that life must be spread in space, and you have to wait another decades to try to put a basis on that. And that's when with Galileo, of course, and then Newton, who demonstrate really with physics that everything in the universe is controlled by laws, and the laws are universal. And that's why actually the cosmos has been called universe, because that's the place where the laws are the same, common. And that's been a huge thing. I'm not going to refer to that anymore, not to say it's not important, it's fundamental, but I just assume that everyone knows that. But just to give you an idea how finally, after the proposal of Giordano Bruno, that because sun are stars and because there are planets around sun, there should be planets around stars, he said, well, they necessarily have everywhere in space the same thing that we have here, so Earth is not unique, Earth should be spread over larger in space. And all the physics afterwards, because they consider that the same laws, that's a syllogism of course, produce the same effects, they consider that finally Copernicus and Giordano were right proposing that. And of course it's a little too dogmatic from my side to say that 4 centuries of physics essentially had come as a goal really to assess that was right, but that's really what they said, that all what you can observe in the universe can be understood by essentially 4 interactions, as we say now, and the same laws apply at all scales. And if that applies on all scales, the question is, do you have the same effects? Are the same laws responsible for the same effects? And is it true because of that, that life should be spread in the universe? Well, actually, in our societies, what we call the Occident, we love unification. We love to have only one response to one question, one response to classify things. And because of that, even the physics love to unify things. We like to see that the 4 interactions actually were 3, and before 2, and before essentially only 1. We love to have that sort of trend. And this unification is even obvious now when you see planetary evolution up to recently were really considered as exemplary of what you see right now. So what you see for the Earth, what you see in the solar system could be extrapolated to large scales. Exactly because of that, we love that same things apply everywhere. And what we call the cosmological principle is exactly that at same scale, everywhere, the same principle apply. So just to say rapidly that all what was initiated in the 16th century applied with a physical basement now up to the origin of the space era. And when we had what I said before, Sputnik, then the Luna, and then all the things that we will see happen afterwards, we start that with the idea that the dogma was right, because now we have a physics assessment that was true, and so that's the way we should look at. And so where we start that, So it's not that long ago. We consider that probably that was right. Not only the Earth is standard, but we have really plurality of worlds in the universe. So that's where we were. To rapidly, and you see why I put that as a context of the exploration afterwards, because if you go up to the end of my lecture today, you will see that we are now in a situation where we probably consider that, for reasons that we understand, that was a misunderstanding of what really are Earth, planets, and life even. Anyway, the starting point of the space activity was with these dogma accepted as such. Just for you to realize a few steps further, I said that the Soviets went to the moon only 1.5 years after the Sputnik. The same second year, they sent three, actually in 59, they sent 3 probes to the moon. One was absolutely fantastic. It was the third one, the Luna 3. Why? Because they decided not only to get to the moon, but to go around the moon. I mean, to target a place distant from the moon at a distance and a velocity so that it could be trapped as a satellite around. And for the first time, they had the possibility to go on the other side. And so, thanks to space, to observe something which is not visible. And so finally, space has been demonstrated as being capable of giving images of what you cannot see from the Earth. And it was that. And this, what you see on the right side here, is the very first image ever taken in space by a mission, by any sort of mission, which was of course a robotic mission at that point. 59, October 59, it was to celebrate the second year of Sputnik 1. Things went very, very rapidly. And what is amazing, but that's not the goal of this lecture here, is to understand how technically they did in a few months only conceive and build the first camera, the first space camera, something that will take pictures and not send back the picture itself, but to translate the picture into a wave. And this wave, we receive it as a TV wave, and then we do the deconvolution here and we go back to the images, and that's what's here. I'm not going to elaborate on that except to say that this image is really fantastic because they didn't do only the opposite face, the hidden one, because they said if we don't see anything, we will never know whether there was nothing to be seen or not. So they decided to make a 3/4 sort of view, to have, which we see on the left part here, some what we call the mare, as we said, the black spot here, which are the mare that you can see, they are visible even with the naked eye. And you see that on the other side, the far side of the moon, there is none of them. And that was one of the first discovery that the moon, the two sides of the moon are different. And again, it's beyond the scope of what I'm going to say today, but that was the first thing that we had to understand and explain that we do now. Why do we have no mare on the other side of the moon? It's not trivial, actually. And so, from 57, then Laika, then the moon, then everything. And finally, there has been something fantastic that only at that time, in 59, Korolev, which was really the head of the astronautics in Soviet Union, said, well, now we can really consolidate our plan, everything works, the rockets works, whatever, we are ready to recruit cosmonauts. And as you know, they did. For 6 of them, the 6th flew, and the first of them was Yuri Gagarin. And that happened April 12th, in 61, so exactly 60 years ago. We should have celebrated that even more than we did actually a few weeks ago. And so Yuri Gagarin was really the first human being in space, and that's what I say, the first exobiological human being really, because he was in outer space, not in the outer environment, of course. It was terrestrial air, but still it was in no gravity, and that's very important. And of course, all these premiere was done by Soviet Union at the time of the Cold War, and everyone in the States waited for how shall we regain the leadership there. And 61 was exactly the year where in January Kennedy was elected. He's been elected before, and he was really elected as the president starting in January 20, 51. And everyone waited, okay, what do you do now that you received this message from Soviet Union? It's the Middle Age, and the Middle Age does better than we do. And so he did something absolutely amazing. He decided, as everyone knows, and you can really hear, because now it's recorded, what he said in May, it was May 5th if I recall well, this famous discourse where he said before the end of the decade, so in the 60s, there will be an American on the moon. He launched the Apollo program. And because he launched the Apollo program, as his response to Gagarin, that has been absolutely amazing. It's one of the best decisions they ever take in space. Why? Essentially because there was no, in 61 when he claimed that, it was just infeasible. We didn't have the technology. They didn't have the technology to get to the moon. They had to build the most impressive rockets, such as Titan, 100 tons in the Earth's orbit. As you might know, no one ever did the same since they are starting to rebuild things like that, but they lost all the knowledge because of the space, because of the STS, the shuttle and that sort of thing. So they did that, and I'm not going to summarize all of that, but it was really a great venture of space exploration because actually, as you know, although they had 3 people who died in 66 for the first Apollo 1, they continued. As of course, it's been a big success that Kennedy didn't see because he started that in 61, and as you know, he's assassinated in Dallas in 63, so everything was done without him, but he accepted that. And the focus I want to put here is on 2 things. One is on this picture. By the end of 68, December 68, so before the 69 where they launched Armstrong and Aldrin and Collins to get there, in 68, they wanted to test all the subsystem in orbit that would be in orbit around the Earth and around the Moon, and they decided to do that in orbit around the Earth just because they didn't have at that time ready what we call the LEM, the module to get down to the Moon. And it happened that the CIA decided that, well, was afraid that the Soviets would just send a zone thing that made a close flyby of the Moon, were ready to send people on the Moon. And they said, no, we will not be also done on that case. We want to be the first, at least to get to the Moon, even if we cannot go down to the Moon. And so the 3 cosmonauts that you see here, Bowman, Lowell, and Anders, have been launched to get not around the Earth, but around the Moon. And that was the first time human beings left the gravity of the Earth, frankly. And that's amazing because, of course, everyone knows this splendid picture which they took around the, when you see a sunrise of the Earth, an Earthrise with the Moon on the what? Comment on dit premier plan? Foreground, background, foreground, yes. But to me, the important thing is not that one. The important is what they did on the way to and on the way from. From the first time getting to the Moon, they saw the Moon, they saw the Earth as a rounded planet, as a rounded ball floating in space freely. And that was still at the time, plurality of worlds and demonstration of the Earth was just a trivial planet. They had the picture of that. And what everyone at that point, for this one, on the way one, on both ways, understood from this picture is not what we now understand from this picture, that the Earth is not as the others. The Earth is very different from the others. But the dogma, the ideological pressure was so high that the only thing the people wanted to see there was the fact that the Earth was exactly rounded. Up to that time, if you look to what we call the cosmogonic book, up to 68, 69, 70, we demonstrated that the Earth was round. Today, of course, you won't do that because everyone knows the images from space because of the meteor, whatever it is. But at that time, it was not the case. So these images were sort of fantastic because of that. And of course, afterwards, you have the arrival in July with Armstrong, Aldrin. Of course, the one we see here is not Armstrong because he was the one who took the image, of course. So he was already down. So that's Aldrin getting out. And this is the famous, that's Armstrong actually. That's Armstrong fit on the Moon there. Which is amazing. And that was really what I think I put here, the first exobiological step, the famous giant step. And here they are studying with the Apollo 15 and 16 and 17. They even had a rover to get rather far from the LEM to get samples. The important thing that will be my last word on the Moon here today, that they brought back 380 kilograms of samples from 6 sites. At the same time, actually, the Soviets also sent rockets and automated system on the moon, and they collected automatically samples 3 times, including the last one, the Luna 24, which is very important because we understood from what we learned with the Apollo mission that because of the impacts on the moon of meteorites and micrometeorites, you have a stratification like that. And if now you get at the top here, and if you take a sample which is rather deep below the surface, it was at the surface long ago. And typically you have 1 meter for 1 billion years. So if you have the capability to follow the grains over 2 or 3 meters, you can retrace really the 2 or 3 past billion years of interaction between the moon, which has no atmosphere, and the environment, interplanetary medium, including the solar wind. And so that has been very important. And the way to do so is to make a carrot, a drill to drill a core. And they drill a core, the Soviets with Luna 24, and had very clever ways not only to drill it, to take it back to the Earth, but you cannot take a 3-meter long drill core back to the Earth, crossing the atmosphere. So they rolled it, and when they unroll it after the recovery, you could extract grains centimeter per centimeter and reconstruct all the stratigraphy. And that's how, thanks to these, we could understand the evolution of the solar system as seen by the sun itself. But of course, the core was with a 380 kilogram of Apollo samples, which are still being studied now, actually. Only a fraction of that has been distributed to the different people. You can really ask samples if you have a dedicated experiment to do, and it will be studied and possibly selected, and you will get Luna samples. There are many, we do not take the measure of what has been observed and found with the samples. It's really amazing what we could do in the lab thanks to the analysis, the very refined analysis of these. One critical results, and that's the only one I want to say, that it was so precious that everyone has amplified, enhanced the capability to make very specific measurements. And one of them was the datation. We could date all the samples we had in the lab, meteorites from whenever they were, the Earth, of course, and now the moon. And the real results was that all the numbers we got demonstrate that all the bodies in the solar system formed exactly at the same time, within a few million years, 4.567 billion years ago. And we knew now why there is a million of years difference. It's really just track the difference in times at which the different bodies formed, but it's a very small fraction. And so it demonstrated that what in the 19th century, 18th and 19th century has been proposed as a model, like the famous nebula model, that is the collapse of a single cloud who put the sun in the center and planets around. That was right. And now it looks trivial, but up to the Apollo missions, there has been another scenario proposed, what we call the catastrophic scenario, in which all the different planets were formed at different time by ejection of material from the sun and recondensation afterwards. We didn't know the age of any of the body of the solar system. With what we had the possibility to measure a very, very tiny fraction of a grain and measure the age at which it formed, we could demonstrate that the solar system is really truly a system. And that was one of the outcomes, but there has been many others. One of them, and I will say in a few minutes, concern the origin. I can just say one thing. At the time of the Apollo mission, there were 3 scenarios for the origin of the moon. We got back the samples, we analyzed them, and it happened that none of the 3 scenarios or models were right. We had to invent a 4th one. And the 4th one has been proposed by Americans first and then others in the late 70s. And as you will see in a moment, it's sort of fundamental because you understood that the moon has been formed as a result of an impact on the Earth by a big body, and so that modified entirely the dynamics of the solar system we had. But more than that, as you will see, it demonstrates that most of the properties that we are dealing with for the Earth now directly originate from the specific impact that we had. I will go back to that, because if we had a different impact in terms of the mass ratio between the impactor and the proto-Earth, or different velocity or different angle or whatever it is, we would not be here, because all the evolution of the Earth would have been different. I will go back to that because it's fundamental. So that's just to say how progressively the analysis of the planetary bodies, starting with the Moon, has been so fundamental. So that's where we are now. And the idea that it did not, with the Apollo missions, it did not broke the dogma that we had before, which is that up to the space era, as I put here, we had only one planet we could work with, really, because by telescopic things you have a few information, but no more than that. The Earth was the only planet we could really study and extrapolate the properties elsewhere. And because the dogma of unification that I already said a few words about were here, it was really understood, but I put some question mark, that Earth was probably a generic and solid planet, and so life probably spread in the universe. So that's now we are typically back to the late 60s, early 70s. And the idea also we had, which also something that you should realize that it's not true, is that the evolution was considered as like an arrow going from simple things up to complex structure. That evolution in space, and we would be there, would be just a matter of getting to increasing complexity. Very early on, we had very elemental particle, quarks first, and then proton, neutron, whatever, and then atoms when the universe cooled down, then molecules in given environments, and then organic molecules with carbon-rich material there. So that was the idea, and rapidly life was put in that evolution as a generic step of evolution. We consider that life is not something that went from, I don't know, that life was just a continuous process of complexity that produced life on the Earth at least. So life was considered generic and there must be steps somewhere. You just need to have the good conditions, but if there is sufficient candidates, you will have life somewhere else. So this was, of course, in agreement with the question of plurality of worlds, and many people consider that, of course, on top of life, you go to the more complex, and you build a complexity scale for which the brain is at the top. And it's clear why, at the end of the 19th century, it was important for people to propose that sort of arrow-based evolution in which you put man back to the top. One of the things important, you've got to realize that with Copernicus, who proposed that the Earth was not central, and then Darwin, who demonstrated that man is not at the top of central position. It's just one among many others, and he explained the reason why by the selection process of the evolution of the living matter. People wanted to have something to put back the brain and man on top of the nature and top of everything. So they built a complexity grade in which the brain would be on the top. And that was, and still is actually, up to now pregnant. It's really something that we have to take the measure and take some distance with that. And I will do that. So all that is goes with the plurality of words. And because life is a generic, it's spread over everywhere. And so what we know from Earth should be extrapolate to all the other planets. And that's what I sort of block here or sketch here. From a single point, which would be in that case the collapse of a cloud, you have several planets, but should be life everywhere in the universe actually. But now something else went. The question of water capital to life. That's something very strange, that all the time, now we know why water was so important to build life on the Earth. We know the reason why. It's not a trivial thing actually. But over the time when the people didn't know the reason why, which has to do with the structure of water, the water molecules, more importantly, the people consider that, and so if life is spread everywhere, then you should also have water spread everywhere. Just a remark here, I will go back at the end on that time. Even now, most of the people consider that the famous concept of habitability is directly connected to the possibility for water to be stable as a liquid. And most of the people who look at habitability, that's the reason why I do not like really this concept, and I will go back to that. Habitability is really considered only focused on these thermodynamic questions, whether or not water is liquid. And we have a lot of books, papers, whatever, saying, well, you have a habitable zone around a star, and the question is whether or not you have planets within it. And if you have a planet within it, it means that water could and should be possibly liquid there, meaning that if you have liquid water, you should have life. And that's still there. Anyway, because life and water are coupled, water should be spread also at a large scale. So exactly as I put life, water should have the same pattern here. And it happened that Mars, being the most favorable candidate, I might go back to that, but if not, you can imagine why. It's not that far, it's red, so if it's red, it's probably oxidized by liquid water. So all the things have been said before being tested, actually. And we have rewritten the story of Mars, and so it's much more complex than that, but at least people consider that that should be the case. So in the solar system, Mars would be the most favorable candidate, and not only it should have life, but water also. And so because of that, along the past century, a lot of people have considered that we should go to Mars because Mars has liquid water there and possibly people even living there. One of the most quoted pictures is that from Schiaparelli in 1877, who with his telescope looked at straight line, and he had the stupid, he called them canali. But just because in Italian canali doesn't mean something made by man necessarily, it could be also a geological structure here. It just meant that there are water running here. We know now that it just demonstrates the limit of his telescope capability. It's an optical disaster, but still, that's how it is. But the wrong thing that Flammarion on one side, who wrote a book on that, and then Lowell in the States, in Arizona, consider that it's demonstrated that Mars not only is habitable but inhabited, because he said the canals there are the way water from the polar ice is used by the people who live close to the equator for climatic region, but they need some water, and so they take all the water from there, and so it's really made by them. And so thanks to that, Lowell built the most prestigious astronomer center in that time, and it's still a very important site actually for astronomy. So life and water, Mars, as you know, it's still it's very controversial, but it's still something that the people would like to see happen. And the validated, the paradigm was present until the US wanted to validate that. And so as soon as it was feasible, they built a mission dedicated to that, and that was the Viking mission. It was a splendid mission. It was a double mission, Viking 1 and 2, to be launched in '76, and actually they wanted the mission to arrive July 4 to celebrate the second century after the Declaration of Independence of the United States. And so they did that. The two worked. It's more than 600 kilograms. It's a huge bodies who went there. But when you look at the reason why they wanted to do so, it was not to search for life. Because again, even when they launched it, by the end of the 60s, to arrive in, they launched in 74, but they built the mission by the end of the 60s, everyone was absolutely convinced that life was spread over the universe, and so again the probability of Earth was really the way to think. And so they did that, and that's a fantastic view that I like to see for myself. It's an actual picture taken by Viking, and you see the arm, which is here. You also even see how the arm has already taken some sample. But again, what I have not finished before is to say that the goal of the mission was not to demonstrate that there is life on Earth, on Mars. It was to demonstrate that not only you have life, but you have a given metabolism. And 3 out of 4 of the experiments on board the Viking were to know, with ingredients feeding the samples, whether they would absorb the CO2 and release the oxygen, or whether they would absorb the oxygen and release the CO2, as our plants or animals on the Earth. So that was really the goal, and they did it. And really the instruments were fantastic, and it is really, truly the first exobiological mission ever made by man on this planet. So that was really fantastic. And as you know, the results demonstrate that you do not need any biology to explain the results. And most of the people, not all of them actually, but most of the people consider that there is no non-ambiguous detection of living activity on Mars. When we know now where they landed in these 2 deserts, so arid, so it's even amazing that they thought at that time that there could be any trace of living organism there on the top surface. Even the UV arrives at the surface and breaks every big molecule here. So anyway, that was 76. It's not prehistory. And as I say here, it was the first really serious questioning of this concept of plurality of worlds. Because really Mars was considered, and it's read, as you see, that it was really the most favorable case to see life there. Just to stay on this picture rapidly to say, it's only rather recently with the Mars Express mission in 2004 with in particular one instrument, the Omega instrument, that we had the capability to measure, not only to image, but also to measure the composition of what we image. And looking at that, we demonstrate that actually the redness here is done by the oxidation of ferrous to ferric, so that's true. So you have Fe2O3 for those who like to see the formula of that. But at the same time, we demonstrate that there is no OH at all there, and it's only anhydrous Fe2O3, and it's not been oxidized by liquid water. It's been oxidized probably by a very tiny atmospheric interaction that requires billions of years to only affect a few tenths of micrometer. And as soon as you get down, you can see, 1 millimeter or even less, that you have ground material which has not been oxidized. So it was true that it has been oxidized. It was wrong to think it's been by liquid water. And actually we demonstrate that everywhere red on the planet has not seen liquid water, but there has been some water prior to this oxidation in many places on Mars. And that's where now we try to get the missions going to see whether very early in the history of the planet we had the possibility to have at least the start of an evolution that on Earth led to the living organisms. So the paradigm has been not validated, but still, and I put that here because everyone who works now with the missions to Mars know that NASA has not really changed its motto, which is always follow the water. This question of coupling the water and life is really pregnant. Okay, I will not be long on these two things. You can really read them on there if you download the things. It's just to show why and how NASA keep this idea that as soon as you have the sign that has been water, immediately for them it means there is life. And not only life, is go to the end here of what he said here. He said, the question is not only to know whether the life, do we have microbes, and more than that, ultimately, can we get there and live? And so that was when they, after the first opportunity, the detection of sulfates over there, and then more recently in 18, so only 2 or 3 years ago, when they had to stop one of the very fantastic mission, the Kepler mission. We'll go back to that in a while, trying to characterize the exoplanets, the planets around other stars, not the Sun. They had to stop it after it's been there. It looked for 2,600 planets, probably what they call discoveries. And what I put here in red, it said, okay, they could be promising place for life. Why? Just because they had the right distance to have liquid water. And below that you see again exactly that. There could be liquid water, and so it's a vital ingredient. It might pool the planet's surface. Always this question of coupling life and water. Interestingly, that was in 76. After this Mars breakdown of this dogma, the question was, where else in the solar system could you have liquid water running now, presently, at the surface of any body? And the knowledge we had at that time, in the early 70s, telescopically, of all the bodies, demonstrate that there is only one single body in which you could expect that there is liquid water, and that was Titan, which is the larger Saturn satellite, close to the size of our planets, our inner planets. And why that? Essentially because telescopically, when you observe the light from the Sun reflected and diffused up to you, only one component absorbed there, and so you could detect him by the absorption. It was methane, CH4. And methane has a strong infrared absorption, and it was there. And so because of that, they say, well, fantastic. Of course, Titan, like Saturn, is 10 times farther away from the Sun, so 100 less energy per unit time. So what do we do? If you have big greenhouse gases, it will be longer, but temperature will start to raise up to the point liquid water could be liquid above 0 degrees C. And so thanks to that, a fantastic mission that was the Voyager mission was decided in 1977. It has to go very fast because to arrive at Titan, not in 20 years but only in 4 or 5 years, they had to use the other reflection from some gravitational effects on the other planets to get there rapidly. That's what they did. They had two missions, Voyager 1 and 2, but the goal really was to get to Titan, not only to Saturn but to Titan, and to make a very close approach to look at things. And I remember the slides that NASA showed at the Congress in the US to make this mission approved, and you saw geyser and almost dolphin jumping out of Titan. So they did a fantastic mission. I will show in a moment one other slide that they did on the way to when they went to Jupiter. They arrived at Titan. The camera was fantastic. They point at Titan, very impatient, eager to see if there is something, and that's the image they got. You couldn't see anything. They said it's impossible. The camera broke just when we decided that, so they turned it back to Saturn. Splendid images, exactly the same red thing that we have on Jupiter. They go back to Titan, nothing. And they understood that it's not that the camera didn't work, that there was nothing to be viewed because Titan is not covered by essentially methane. Methane is not 90 or what percent, it's only 1%, and all the rest is N2, it's nitrogen. And we know that nitrogen is not a greenhouse gases. That's why it does not have infrared absorption. That's why we couldn't know that there is some. It's the only planet with N2 present at that level with the Earth. And now it was understood that probably this planet was not with liquid water. The temperature is probably close to minus 200 degrees C. So no liquid water, and it was really the breakdown on this question of plurality of worlds. Titan is interesting for many other reasons, but not to harbor liquid water. So that was really what happened when we arrived in 81 actually there. But on the way, as I said, the mission made a flyby of Jupiter, and that was really amazing because a lot of things have been discovered. Again, I have no time to discuss that in depth, of course. On the top right here you have a cartoon which has been drawn by Galileo himself. When remember that in 1609 he had what we call a telescope. Actually it was a refractor, and he could point it to Jupiter, and he saw, if you look at that, you will see that night after night, over a week, he saw Jupiter in the center with the famous sign of Jupiter. And the first day, 2 on the left side, 1 on the right. Next day, it was 3 on the right, then 2, and finally 4 on the right side. That demonstrated for him that there was bodies turning around, moving around Jupiter. And for him, it was fantastic because just after what Copernicus demonstrated, that everyone turns around the sun, he understood that gravity is not only exclusive of the sun. Gravity is a universal property in space. And that finally went a few decades afterwards to Newton's universal theory of gravity. So this was absolutely exemplary, the demonstration that there were 4 satellites, what we call now the Galilean satellite. And frankly, from this discovery up to the arrival of Voyager, we didn't know much about that. We had refined trajectories, whatever. We had no idea of what they were. On the picture behind, you can see Jupiter, and at the same scale, the 4 satellites. Of course, not at the same place, but it's exactly the 4 satellites viewed like that at that time. And what we saw here is an amazing diversity. These 4 bodies have exactly or about the same size, typically the inner planet size, between the Moon and the Earth typically, much smaller than the Jupiter itself. And what you see here is that the 4 bodies, which were very likely from exactly at the same point, from the same material, at the same time 4.5 billion years ago, today do not have at all the same status. Down right, the body on the down right here, which is Io, the closest to Jupiter, is a volcanic body with a lot of sulfur oxides giving, when they cool down, the different color that you see here. And the volcanic activity that the 2 Voyagers showed and observed is so fantastic that every single point on the surface of Io is covered by magma lava at every few thousand years, which is really ridiculously limited in time. So it's really it's the most impressive volcanic body in the solar system. On the other side, top left, you have Callisto, which is a body totally cratered at saturation. If you have an enlarged picture of that, you will not know whether it's the moon or when part of Mars or an asteroid. It's really just cratered places as we have everywhere in the solar system. Getting back to Io, just before it, the white body here is Europa, which has essentially no crater. It's just icy with a lot of I don't know the word in English, actually, serac and structures within the ice, as you have in glaciers in the Alps, and there are no craters at all. And the last one, the bottom one, between Callisto and Io, is sort of a mixture of the two with ice and craters places. How can you realize that the evolution of its bodies, again on the same point in space, unified in terms of location, material, date, have so different now? And that's the diversity is, to me, exemplary of what we have discovered progressively, not only at the scale of the satellites, but the planet themselves. To understand the evolution of the planet, you do not need only their location, their size, their mass. That's not sufficient. And we will see that, and that has been the first lesson on that. We need to understand much better what caused the evolution of all the planets, exactly as we had to understand, and now we know why these four bodies have exactly that sort of features now at the top. So not only it's unexpected, but to me it's exemplary of the diversity that progressively, that has been observed in 79, and so you see that in this sort of time frame, we first demonstrate, or it has been sort of not demonstrated, but really indicated that life was not necessarily something spread over at least the solar system. Liquid water was not something spread efficiently somewhere else, like rather than on the Earth. And diversity is really becoming the new paradigm here. So up to the space era, again, we didn't know where and what were the other ones. But space exploration finally put all these bodies within our scientific horizon. We could finally get there and observe these bodies. I've shown one or two of them, but systematically now, everyone until the comet really has been explored over the further decades up to now. And for some of them we have been many times, or several times at least. For some it was only one or two times, but really that's the way we went with space exploration. And now we understand that we belong to one of the evolution, and we start to understand the evolution pathways of the Earth, but now we have the possibility by observation to see how the evolution went for the other planetary worlds and to compare them. So that's really the key of the space exploration. And when we do that, again, the outcome of that is this unexpected diversity. So that's an idea of what the solar system was telescopically. Essentially, the 4 points here are the 4 Galilean satellites, Saturn, everything. The Earth, for example, until before the Apollo 8, the Earth was something, infinite mass below our feet. And so after the space exploration, all these were given fantastic pictures, which progressively are so integrated in our cultural patrimonium that we don't even remember that we didn't know that forever. We only discovered that progressively over the past decades. So unexpected diversity is really the wording that you should at that point realize. And again, these 4 here, which are the 4 on the top here, are the one I just showed. But now what about the Earth? When you look at the Earth now, it's totally different from what we had after the Apollo 8. For Apollo 8, again, it was a standard generic planet on the pictures because it was really the dogma that really prevailed, that prevent that we understood this image differently than what the dogma imposed on us. But finally, when you look at this image here, we have ocean here. They are unique. The ocean cover is absolutely unique in the solar system. Nowhere else now, at least, and probably ever, we had a cover here. Interestingly, the oceans have no time to discover that. They were formed, as you will see, very early on, probably only a few tenths of million years after the planet formed, and they never disappeared. The planet Earth was always covered with oceans. The cloud cover, that I will not have time to discuss neither, but it's very strange, because when you, of course, the covers are what is white here. Why is it white? Because the picture is taken out, much farther out of the clouds, and so they reflect, all the clouds here reflect the solar light here. When you have a big cloud, like a cumulus cloud, it reflects something like 50% of the light that goes in. So you understand that by 50% of reflection, if the total cover of clouds were to change over the time, from 50%, which is typically what we have now, to, I don't know, even only 40% or 30% or 80%, it would make a huge variation of the temperature below the clouds at the surface of the Earth. And that's not seen and not observed, because if we had that, of course, there would be a record of that. So not only the cloud coverage is some sort of like a 50-50, but that's unique in the solar system. Venus, for example, it's 100 cover. The cloud coverage of Venus is such intense that you do not see, and you cannot see the surface. And if you were at the surface of Venus, you would not even see that the sun exists. The lunar light doesn't go through. All the others essentially are cloudless. On Mars, you have some clouds formed in the afternoon that disappear in the morning, but the Earth is a 50-50. But not only that, it's a stable 50-50, not at the time scale of days or weeks, of course. We know locally that there might be, but globally, on time scales much longer than that, thousands, maybe millions years, maybe more, it's this. We don't know yet the reason why. We have not yet understood the process, which is a very complex process, because clouds nucleate on very small things. We don't even know on what they nucleate. It could be small grains from comets in the stratosphere. It could be particles from the cosmic rays. Depending on the nucleation site, you will have different clouds. They will not sustain the evolution, the day-night evolution the same way, and so on. And it's fundamental to understand that now in the course of the coming years, because the coverage of clouds might be the only possibility for the increased climate now because of the anthropic evolution to sort of not speed up but speed down the evolution of the climate by putting some of the water that will necessarily be evaporated more as the temperature rises. If some of the water, instead of, it's a greenhouse gases of course, instead of getting only in the atmosphere, also condense a little bit, then the condensation might increase the fraction of the input solar light reflected, and so decrease the increase in temperature. So anyway, that's another lecture. So atmospheric cover also is something that is absolutely unique, and the question now is, at what time and space scale is it unique? And of course, the same question for life. Is life unique? And is it unique in time scale and space scale, at wide scale, like the galaxy or the solar system or the universe? So that's really the outcome of what has been done with the space exploration with respect to the diversity. But very interestingly, at the same time, starting 20 years ago, at the same time where the Earth started to be something which was sort of unique, we start to discover that there are exoplanets also in space. And when I say we, it's another community who did that, started in '95 for the first discovery. And now we have more than 4,000 exoplanets detected, and most of them are already characterized. The idea of that, again, there are planets around stars, as I already said today, is an ancient one, because a lot of people proposed that, but there was no way to validate it. It was just an idea. And what has been done in '95, that they validated the concept itself, because now we are convinced that most of the stars have planets around. And so, as such, of course, it's a major result. But beyond this confirmation, there is something which I consider more important, which has been discovered by these two, Michael Mayer and Didier Queloz, who had the Nobel Prize for that, as you know, 2 years ago, 3 years ago, which is that none of the systems that they have discovered correspond to what could have been expected. And that's something absolutely amazing, that the same diversity that we finally realized within the solar system as the result of the evolution from a cloud that contains 2 planets, the same applies now from the solar system as a whole. Nowhere else have we found a stellar system similar to our solar system in terms of the content. Inner planet, giant planets at the same location, this and that. And the diversity is really the way to... so similarly to what we had here, diversity within the planets and expected diversity, now we have exactly the same for the stellar system. We belong to one, and we know it, and we start to understand it, but now we have the possibility to access to the other, and when we look at the other, what we discovered is the diversity also. So the paradigm of plurality of worlds is moving now to that of diversity of worlds at all scales. And the questions are now, what are the processes which drives this diversity? And as already alluded a little bit, it's not trivial. Then the second question that we will touch, is life now, as we saw it was proposed as a generic product of the complexity increasing, is it really true? And are we sure that life might have emerged anywhere else than on Earth? And that's the topic of the rest. And within the past 2 or 3 decades, the space exploration has really modified entirely our conception, understanding of what drives the evolution of planet, of the Earth, and as we'll see, probably of life itself. First question, what drives the diversity of evolution? That's not a trivial thing, because now, and I demonstrated that, or it has been demonstrated with, as I said, with the lunar samples, we are convinced that all the planets come from the collapse, autocollapse, or self-collapsing protocloud. So the same cloud formed the central star and all the planets around. So there is a common origin. But I put common in quote marks because if it was really common, in a sense, exactly the same initial conditions, we should not or could not have that happen. So what really do that? I just summarize that in a sentence, and I will try to explain the sentence with some example afterwards. All the processes that act, like gravitational things, impacts or whatever, are generic as processes. It's not that one planet invented some process that does not apply for the others. The processes are entirely generic. And so what has been discovered and proposed by physics all around the past centuries is right. The processes are identical as processes. But what is new is that the processes do not drive the evolution by themselves, because the processes can take different forms contingent to the context. And these are the good players for the diversity. And this is what I will now try to explain, because that's something rather new and it's sort of easy. And for this I will take 1 or 2 examples within solar system, but also it will apply to stellar systems. So, and the 2 examples are, one is migration, the second is giant impact. So let's go to the first one. I told you that the solar system as we have it now is schematized here. We have the inner planets, per definition 4 of them inside, and Jupiter and Saturn much farther away that it's shown here. So we have really giant planets far and inner planets in the center. So the question is, why do we have that? And up to the discovery of the exoplanets, and you will see why, we think that there was a single and easy explanation for that. If you go far from the sun, the temperature decreases, and there is a limit, what we call a snow line, beyond which water is no longer stable as vapor. It's solidified as ice, actually, but they say no, it's an ice line, we should say. So far away we have ice, and inside we have essentially vapor, which is what is summarized, which is sketched here. In blue it's the ice, and inside it's water vapor. Why is that important? Because if you have water ice, you may have giant planet. Why that? Because if a planet is giant, it's because you created a lot of gas, you have huge atmospheres, but the atmosphere in the disk initially has been also swept rapidly by the sun itself, by the early sun. So you had very rapidly to accrete gas to do so. And if you do that inside, close to the sun, only with the minerals which are there, because you have no ice inside, you don't have sufficient mass to accrete a lot of gas. So that's why the inner planets have only very tenuous atmospheres. Well, up to 100 bars maybe, but it has nothing to do with what Jupiter and Saturn, Neptune and Uranus have. So if you are far away, you have a lot of ices, water, methane, everything is already condensed, and then you can rapidly grow a nucleus, which was a core, which would be 10, 20 times the mass of the Earth, sufficient to accrete a lot of gas. So that's why we understood that giant planets must be far away when the temperature is low, when ice is present, to accrete the gas. So that was the situation here. But it happened that the first ever planet founded was a giant planet, close to Jupiter mass, hundreds times the mass of the Earth, but it was found, this very first, and many others have been found, 10 times closer or 8 times closer than Mercury is from the Sun. It's very hot at that point. It's impossible to have ices stable where the giant planet has been formed. So that's why it has been really a fundamental result to find not only that you have planets, but different from what we expected, because we would never have expected. Only a few people had proposed that before, but they were not really taken into consideration, unfortunately. So yes, we had giant planets very close to the stars. And how can we... And the idea that they have been formed far away, for the reason I tell you, they have to form, but then between the time they were formed and we observed, they essentially migrate. And this question of migration is fundamental. Of course, it doesn't go as my arrow showed. It spirals around thousands, billions of times, of course, like that. But while doing that, it enters progressively, it spirals down to the central thing. That the planet goes directly to the stars? Possibly, but only on one condition. Because what caused the migration is the interaction between the planet and not only the stars, the central star or the planets, but also the gas in the disk. And this is what has been underestimated by the people who made the computation, that you have gravity between the planet and the disk itself. And so until you have some material in the disk, you will migrate. But if by chance, I would say, the disk is totally swept out, when the giant planet is not too close to the Sun, a fraction of the Earth's Sun distance actually now, then it could be stabilized during billions of years. So that's what's happened. If all the stars do not go directly to the Sun, because it might take too long, and they will stop when there is no more gas and grains actually in the disk. So the question is, when you have this sort of migration, what does that do for the disk itself? And the answer is, it does not do much if it's so rapid that the gas is still there and it has not really accreted already and grown into what we call planetesimal. But if we have started, because it took maybe 1 million years, a few million years to start, it's in million, not in billion, million years to start, then while it goes inside, you will have something very important, which is sketched here. As a function of the entrance of the planet within the system, it essentially cleans out, expels a lot of grains outside, well, inward or outside. They can either go toward the central star or be ejected away. And this ejection essentially clean all the disk, and if you do so, and if it goes very close, you have no more matter, just to have inner planets accreted afterwards. So you see why this migration is fundamental to understand the further evolution of the bodies within the disk. It's really a matter of how it did. And then you can already see the conclusion I will have in a few minutes, that you have all possibilities for migration to behave, and you might have some which will end up like that, but you might have a lot of differences. And actually the question now is, we have Jupiter and Saturn far away now. Is the fact that we are present and the Earth exists, and with all what happened on the Earth, is it a result of the fact that Jupiter and Saturn has not migrated? And if that's the case, why would that be? Because migration seems to be a very generic process. And so why would we be, if I can say so, our solar system, very specific on that? And actually, it could well be that also Jupiter and Saturn did migrate, but in a very specific way, because all the migration are specific. It's not that it's a specific, the others would be identical. No, everyone is specific. And this has been proposed by colleagues from Nice, and Alessandro Morbidelli being the lead of that, in what they called the Grand TAC model. And I will take a few minutes just, or I will be fast, I hope, to explain to that. That's already 10 years old, so many other models exist and so on. But it's exemplary of what could have happened, and that's very important. They start with the mass distribution of the inner planets. As you know, we have 4 inner planets, from Mercury to the right and the Sun more to the right, and then you have Venus, the Earth, and Mars. What is very strange, that Mars is very small in size, 10 times smaller than the Earth. And the question is, what does that translate? After the accretion, probably before the evolution, it should have been something like that, same size, but no water, no tectonic, nothing yet, because it was too early on. So 4.5 billion years ago, you have something like that. But actually, the people realize that when you make a model by calculation of what would be an accretion pattern if the disk was homogeneous, you should have mass at least the size of the Earth. So how do you go from this modeling in a disk full to that which is the reality? And the idea that to have the planets with the right mass distribution, you have to start your accretion from a disk that will be not empty, but confined, and confined in the center below a distance which is somewhere between the Earth and Mars' present orbit. And so the Grand TAC model tried to account for that. And the idea would be the following. Jupiter, again, was formed far away because it had to be above the snow line. And then it started to migrate. And doing this, he entered while he was cleaning the system. But at some point in time, Jupiter was not the only body formed in the outer solar system. There has been others, one being the Saturn. And it happened that Saturn formed farther out, as you know, and that's why it took longer time to get this core made. But it very rapidly swept down because most of the disk was already swept. It was cleaned. And Saturn arrived at a distance from the Sun when essentially it's called what we call the 3/2 resonance. Jupiter makes 3 turns when Saturn makes only 2 turns. So regularly, Jupiter and Saturn are in the same position. That's what we call resonance. And when you have a resonance, they block in that, and they will do everything afterwards in that configuration. And this configuration, resonance is the same when you tune your TV recorder or whatever, just to have something. Something is modified. It could be the intensity, the eclipse, whatever it is. In that case, what has been computed by Morbidelli and his team is the following. Just because of the mass ratio of Saturn and Jupiter, if it has been different, it would not be the case. The two decided, if I can say so, not to continue the migration toward the Sun by, again, on the other direction. That's what they call the Grand TAC, because they decided to change the direction from inward to backward. And so they went back to where they are, leaving the confined disk. Of course, it's not so straight, so I put that here to demonstrate that it's something continuous like that. If Saturn had been less massive, it would not have been able to stop Jupiter, and Jupiter would have gone in there in the center. We would not be here to talk. If Saturn had been much higher mass, with a higher mass, more heavy, both of them would have continued, and so we would not be either here. So it's really the ratio of mass plus many other things at what time it arrived, which depends on the form of the disk and that sort of thing, that decided that finally we had a confined environment of that size, out of which finally you could accrete the 4 planets as they are here. You modify something, the time Saturn starts, the mass of Saturn or whatever it is with respect to Jupiter, you will have an entirely different configuration, and all the rest of the story will be different. So again, the mass distribution is the right one because the double migration was was specific to. In other words, the mass distribution is directly dependent on all the parameters that drove the double migration that we had in this model. So that's what I put here. The solar system migration is highly specific, and that's demonstrate what I wanted to say here, that the contingency that shape really the generic process. Migration is a generic process, but every different migration will have a different shape, and the shape is responsible for the diversity of the evolution more than the process by itself. But now we have a problem, and the problem is that if that was the case, if the inner planets would be created only from the inner material, as I said, in the inner material you have no ice, there would not be water here. We would not have water to drink, to make the oceans, whatever. So the question that where does the water comes from? And if we had only vapor, it would not work. Water comes from the outer solar system exactly for the reason I said. Outside you have ice, and not only ice, but ice and many other volatiles, carbon-rich species, and as we showed in the comet themselves. So water and organics come from the outer solar system, from comet-like objects. Of course, by turbulence, some of the material from inside also goes outside, so you have some mixture, and that's what has replenished the asteroidal, the asteroids area. So you have these double things here, and this is sort of schematically scanned here. The water went during the accretion itself. Some of it could have come later when the body were finished, but some of that were between during the accretion itself. So at the end of the accretion we had bodies which were essentially made of minerals created from the inner place, but also grains coming from the outside. And the question is, how do you get this out of that? How from this you can build the water-rich planet that we have here? And so the insertion here of the right mass does not tell you that the water immediately will go to the surface. So how the water went to the surface, and here I dare to give a suggestion, which of course has been discussed in many within the community, but it's still very controversial. It could be an effect of what we call the giant impact that I already mentioned. Giant impact is what? It's the fact that after a few tens of million years of accretion in the disk that I just showed, you didn't have 4 planets, you had maybe tens of proto-planets about the same size, big things like Mars, proto-Mars, proto-Earth, but tens of them. And they were so turbulent, the disks were so turbulent that there has been a lot of impact from one to the next. There is a lot of collision there. Most of the collision is there frontal like that. Both of the bodies, the impactor and the impacted one, just disappeared. The result is that we had 4 remaining. But these were also highly collided at the very beginning. And now we consider that very likely, and I said that when I talk about the moon, that probably the Earth had an impact by a body that we'll call Theia, which was very big, about what is represented here, 1/10 of its mass, typically like Mars today, or maybe even higher in mass. So this impact had a huge effect of the history, the further history of the Earth. Partial loss of the atmosphere. Most of the atmosphere has really escaped at that point. You have a huge amount of the energy went to heat all the body of the Earth as a magma, so you have a huge magma ocean down to the core, probably. The core of the impactor was mixed with the core of the moon, of the Earth, and so you have a big iron-rich core that with a big magnetic effect here, probably. But fraction of that, given depending on the energy of the angle of the impact and the ratio, the mass ratio of the two, a fraction of the outer part of the Earth were ejected but kept trapped gravitationally as a disk. You have a big circumterrestrial disk, very massive actually, because the impacting body was big, and because again the geometry of the shock allowed that. And it is in this disk that the Earth moon accreted. The moon is a reaccretion of the matter within the disk, and that's explained why a fraction of this material resembled that of the Earth, but many other properties that we found looking at lunar samples. So accretion of there, and importantly, there has been effect of the moon itself on the Earth because of that. One of them, I will say just by maybe one picture here, is illustrated here. The moon has an effect stabilizing what we call the obliquity, which is the angle that the rotation axis around which the Earth turns in 24 hours now, is with respect to the perpendicular or the ecliptic, which is the plane of the Earth around the Sun. This angle, as you know, is 23 degrees, latitude of the tropics now. The question is, why is that the case? Why this? Of course, it's a result of the collisions. But what is important, and that has been demonstrated by Jacques Lascar, an astronomer in Paris, which is a very important discovery, that the Earth stabilized this angle at 23 degrees plus or minus 1 degree over billions of years. And that's fundamental because that has induced a continuous perennial climate which is sort of identical over the time. In particular, the oceans did never evaporate entirely or never froze entirely. They remain as liquid water for billions of years thanks to the moon. And again, it's not thanks to the moon, it's thanks to that moon formed in that condition by that impact with that angle, that ratio of mass between impactor and impacted body and so on. So again, this is an important demonstration of again how a generic process can end up in a diversity of solutions and evolution just depending on the contingents of the parameters that drove this process to happen. And so that I put here, the effects are critically driven by the contingent pattern of the impact. And it is the specific impact that does that. Okay, so these two examples sort of illustrate the driving roles of genericity and contingency toward the diversity. And that explains why the plurality of worlds now move to the diversity, and why, because of that, the Earth, whether we like it or not, is absolutely unique. As soon as we know in details what the Earth looks like, we know that the reason why is the inputs of all these contingent factors during the course of the evolution, the two that I showed today just being example of that.